Welcome. In this video, I'm going to look at just question 11 and 12 from the Topic 5 quiz. So question 11 starts at the bottom of this page, and unfortunately the page break isn't real convenient. But it gives you some information about an anhydrous copper sulfate solution absorbing some water to form the pentahydrate. And it shows you how we could find the heat given off, the heat of this solution, using Hess's laws. So this is one that IB kind of likes, and it's a little bit weird in my mind. Let me just grab my thing here. Is that what you see is that you could go from reaction 1 on the left. Let me just grab a cursor here now. You could go here and then to here, which means you could leave this equation, but you'd have to flip this equation and add them up, and you should know what this is. That's what they're getting at on this question. So if we proceed to the next page, part A says to determine delta H1, a student placed 50 grams of water in a cup, blah, blah, blah. After 2 minutes, dissolve 3.99. Anyway, they ask you to calculate the amount in moles of anhydrous copper sulfate. So they told you it was 3.99 grams. You have the formula on the previous page, so you should have come up with the mass of 159.61. So that's where I got the 0.0250 moles of anhydrous copper sulfate. And then it says determine what temperature rise would have been. Now by rise, I don't think it's clear that they mean the increase, but that is what they meant. But a lot of you just estimated the maximum temperature, and I gave you the mark for that as well. But the fact that it was worth 2 marks should have been your tip that you were expected to do two things. Estimate the maximum, which I estimated up here as 26.4, and then subtracting from the original temperature of 19.1 and coming up with the rise of 7.3. Then part 3 said calculate the heat change in kilojoules when 3.99 grams is dissolved in water. So I've got my 50 grams of water, or if you added the 3.99 grams of copper sulfate to it, that was fine too. IB would accept either calculation. So either 50 or the combined mass of 53.99. But definitely use the 4.18 for water, and then whatever your estimated temperature change was. And finally, dividing by 1,000 to get it in kilojoules. So you should have come up with an answer of either negative 1.5 or negative 1.65 kilojoules. Now, this isn't kilojoules per mole yet because we haven't divided by our molar amount. So that's part 4. What is the kilojoules per mole? Well, we already know it was 0.0250 moles of anhydrous that we dissolved. So I take my negative 1.65 kilojoules, divide by the 0.0250 moles, and I come up with negative 65.9 kilojoules per mole, or negative 60, depending upon which mass value you used. Moving on to part B then, part B talks about reaction 2. And it says, to determine the heat of reaction 2, 6.24 grams of the pentahydrate copper sulfate, and again that formula was given at the beginning of the problem, was dissolved in 47.75 grams of water. It was observed the temperature decreased by 1.1. So first of all, calculate the moles of water in 6.24. I'm not sure why they really want this, other than to show that you know what pentahydrate means, but from the equation, it's pretty obvious there's going to be 5 times as much water because it says 1 mole of copper sulfate plus 5 moles of water gives you this pentahydrate. But anyway, I'll play along. 6.24 grams. The whole pentahydrate, when I add in everything, the copper sulfate plus 5 waters, I came up with the mass of 249.71. So I get 0.0250 moles of the pentahydrate. And since there's 5 moles of water in each mole for each mole of the copper sulfate, I would take 5 times that amount, and my water alone would be 0.125 moles. And I'm not going to use this again, so again, not quite sure why they asked for it. So determine the value of H2. I can either use the 47.75 grams of water, or I can go ahead and add on the 6.24 grams of the sulfate as well. So either mass is fine, but the 4.18 is the C value, and the temperature was only 1.1. Dividing by 1,000, I got 0.220 kilojoules. But this is a positive value since the heat was absorbed. This is endothermic in this case. And then finally, you were supposed to get it in kilojoules per mole. This was all in one step, which was kind of a lot for just 2 marks. But when I go ahead and do that, I came up with positive 8.8 kilojoules per mole. And then finally, using the values obtained for H1 and H2, determine the value. Well, at the beginning I said H1 I can leave because that's going the right direction, but H2 I have to flip. So now I'm going to take negative 65.9 that I calculated for the first one, and I'm going to add the flip value for H2, which was positive 8.8, so it flips to negative 8.8, and that is how I came up with the value of negative 74.7 kilojoules per mole. Then they tell you that the data booklet gives it as 78 kilojoules per mole, and you have to calculate the percent air. So 78 minus my 74.7, my decimal isn't very clear there. My 78 minus my 74.7, just so you're clear where the decimal's at. Maybe a little better there. That's where I came up with 3.3 as the difference. Divided by the expected 78 gives me 4.2%. Or if you didn't have a value to use, they told you to go ahead and use 70, in which case you'd come up with a percent air of 10.3%. So number 2, a student recorded that her anhydrous was pale blue rather than completely white, so suggest why. Well, it means it's absorbed some water, because when it absorbs water, it turns to the blue color, the dark blue color. And how would this have affected the value? Less water would have been absorbed. If less water is absorbed, it would decrease the heat that was released. So my value would be slightly less than it should be since the process had already started. Then question 12 is talking about the combustion of methanol. And we're going to look at a couple different ways to come up with the delta H. We're going to use, I believe it's some heats of formation or enthalpy values, I guess it is, as well as using some experimental values. So again, page breaks aren't real great here, but here's the formula we're starting with. The first way we're going to calculate delta H is, they say, using information from the data booklet, come up with a theoretical enthalpy of combustion. Well, I've got the structures drawn here, the Lewis structures, so we could see our bonds. So I came up with 3 CH bonds, 1 CO bond, an OH bond, and 1.5 O double bonds. That's my reactants, and because we're talking about enthalpy, it'll be reactants minus products. On the product side, I have 2 CO bonds and 4 OH bonds, so I went ahead and reduced my OH bond from the reactant side. But you can see I looked at my numbers in the data booklet, and when I plugged and chugged, I came up with negative 650 kilojoules per mole. Then part B says, here's some data where we actually did it in a calorimeter. Here's our initial and final mass, so I could subtract those to find out how much methanol I burned. Here's the water I used, and here's the temperature change. So on the page, I could calculate the amount in moles of methanol used. So here's my initial and final mass. So I had 0.523 grams divided by the molar mass of methanol. I came up with 0.0163 moles of methanol. Calculating the heat absorbed by the water is just the 20 grams of water times the specific heat of water and the temperature change, and then dividing by 1,000 to get the kilojoules. And then I could take my results from 1 and 2, and I came up with negative 25 kilojoules per mole. Now this is much, much lower than the negative 650 I calculated. And because it's experimental, I can assume there were some massive systematic errors in this experiment, like they must have done it in a glass container with no cover and had all kinds of mistakes. And that's what part C says, is the data booklet is negative 726, suggests why the value differs from the values calculated in parts A and B. Well, part A, we use enthalpy values, so we could blame that because it's based on averages. Bond enthalpies are always an average, so they'll be low. And the other thing you may have noticed is that the CH3OH was given as a liquid in the formula, and bond enthalpies are based on it being a gas. So if it was a liquid, it would require some heat to get it to the gas state. So that is why our value was low, because some heat was misdirected to that process. And then part B, it was way low, so there's a serious flaw. Heat loss to surroundings is always an easy one when you're using a calorimeter. Other acceptable answers on this would have been incomplete combustion of the methanol, or again, if liquid water formed instead of the gas or water vapor, that would also influence the results.